Today we're going to be talking about section 3.4, which is concavity and the second derivative. So we're going to be looking at the effect of the second derivative of a function and how that affects the look of the graph. So first we're going to start with definitions as usual. The first definition we're going to talk about, which is equivalent to the definition in the book, but is not the same, but this definition shows up in some other calculus books, and I wanted you to see it because this is something you might encounter in other places. If the graph of f lies above all of its tangents on an interval, then it's concave up, and if it lies below the tangents, then it's concave down. Now the definition in the book, definition 3.4.1, says that f is concave up on an interval if f prime, the derivative, is increasing. Not if f is increasing, but if f prime is increasing. And the graph of f is concave down on an interval if f prime is decreasing. And again, that's where f prime, not f, is decreasing. And if f prime is constant, then the graph is said to have no concavity. And we're going to look at some pictures to illustrate how these definitions are actually the same. So first, concave up. In the top picture, we see that f is above all of its tangents. And in the bottom picture, we see that f prime is increasing. So here, f is above all of its tangents, and then here, f prime is increasing. Now for concave down, in the top picture, we see that f is below all of its tangents, and then f prime is decreasing. So these are equivalent definitions. Now, we've talked about concavity a little bit now. Last time we were talking about increasing and decreasing. There are 4 possible combinations of concavity and increasing versus decreasing. So if f is increasing and f is concave down, then we're going to get a shape that looks like this, at least roughly like this. F is increasing and concave down. If f is decreasing and concave down, we get something that looks kind of like this. If f is decreasing and concave up, we get a section that looks like this. And if f is increasing and concave up, we get something like this. So now we know if we have an interval where f is increasing and concave down, or decreasing and concave up, whichever one of the 4 combinations we have, then that means the graph will look roughly like one of these 4 things, whichever one of those combinations we're talking about. And now we get to the concavity test. So this is theorem 3.4.1, and the concavity test just uses the second derivative to tell us when the function is concave up or concave down. So if the second derivative is positive, then the graph of f is concave up. If the second derivative is negative, the graph of f is concave down. So we're going to look at some pictures here, and what I have is the graph of f and f double prime, so the second derivative shown together, and the graph of f is in blue, and the second derivative is in green. And what we see here, if we follow the graph of f, this is concave down, concave down, concave down, until we get to here, and then we switch to concave up. And on the graph of the second derivative, we see that it's negative, negative, negative. And now we get a second example here, where again we have the graph of f and the graph of the second derivative. The graph of f is in blue and the second derivative is in green. And we're going to trace along the graph of f. So along here we have concave up, concave up, concave up until we get to right here. And then we switch to concave down till when we get to right here, and then it switches back to concave up. And we can look again and see that we have concave up where the second derivative is positive until we get to here, and then the second derivative switches to negative, and now we have concave down until the second derivative becomes positive again, and when we switch to concave up. This leads us to our next definition, which is about points of inflection. A point of inflection is a point on the graph of f at which the concavity of f changes. So we're going to look at our graphs again. We're going to look at these examples where we have the graph of f and the second derivative on the same graph. We have blue is the graph of f, and the second derivative is the green graph. And right here, we have an inflection point marked where the concavity of f changes from down to up. And notice this is also where the second derivative switches from negative to positive. And looking at our second example, we have concave up, concave down, concave up again. And so we have two inflection points here. The first one, the graph of f is switching from concave up to concave down. And at the second one, the graph is switching from concave down to concave up. All right, now we have a theorem about inflection points. And this theorem tells us that if we have an inflection point, then either the second derivative is 0 or the second derivative is not defined. That's a useful tool for us for figuring out where we might find inflection points. All right, this brings us to our first example. We're going to find where the function f of x equal x to the fourth plus 8x to the third plus 200 is concave up and concave down, and we're going to find any inflection points. You should pause here, follow the link to the YouTube video for this example. There's also a link in Blackboard, or if you are in the non-narrated slides, you can just click the link and that should take you straight to the YouTube video. Okay. After having watched the video, I just want to come back and look at this example very briefly again, looking for the concave up and concave down intervals and the inflection points. And what we found was that f is concave up on the interval from negative infinity to negative 4, and then from 0 to infinity, and concave down between negative 4 and 0, with inflection points on the graph at the specific points negative 4, negative 56, and 0, 200. And I just wanted you to see the graph of f and f double prime, the second derivative, together again so you can see what's happening. So again, blue is the graph of f, and green is the graph of the second derivative. So right here is our first inflection point at negative 4, negative 56. Notice this is where the second derivative is changing from positive to negative. And then we get our second inflection point at 0, 200. And this is where the second derivative is changing from negative to positive. Our next example, we're going to find where the function f of x equal x over x squared minus 1 is concave up and concave down. And we're going to find any inflection points. Again, pause at this point, follow the link to the YouTube video for this example. There's a link in Blackboard also. If you're just watching the regular slides without narration, then you can click the link and it will take you directly there. Now coming back to that example, which you've just watched the video for, I would just want to review again, like I did with the last example. Here we found that the function is concave up on the intervals from negative 1 to 0, and then 1 to infinity, and concave down on the intervals from negative infinity to negative 1, and then 0 to 1, with one single inflection point at 0, 0. And we're going to look at the graph. F is in blue again. The second derivative is in green. And so we're just going to trace along the graph. So over here, negative infinity to negative 1, f is concave down, and notice the second derivative is negative. And then at negative 1, there's an asymptote on the graph. It's not plotted here, but you can tell there's an asymptote there. We switch over to concave up. Notice that the second derivative is positive. And then at 0, we switch to concave down. Notice the second derivative goes negative there. And then at x equal 1, there's another vertical asymptote. We see that. And right there, the graph switches again to being concave up. Notice also the second derivative is positive over there. But I want to point out that although the graph is switching concavity from concave down to concave up at x equal negative 1, and then from concave down to concave up at x equal 1, we don't have inflection points there because the function is not defined. We don't even have a point on the graph at those places. So we can't actually have inflection points. That is only at 0, 0. Okay, our next example, we're going to look at the graph of the derivative of a function. We've seen this graph before in the last lecture. So this is the graph of the derivative f prime of a function f. We're going to figure out where the function would be concave up, concave down, and the x value for any inflection points. In this case, we can't give both coordinates of an inflection point because we don't know what the actual function f is. Okay, for f to be concave up, that means f prime has to be increasing. So that means we're looking at where f prime is increasing, and that's going to start at 3 and go up to 6. And then we have a break in the graph, but the graph continues to increase from 6 to 9. So f will be concave up from 3 to 6 and then 6 to 9. For concave down, that's where the derivative is decreasing. So looking at our graph, that's going to be from 0 to 3. So f is concave down from 0 to 3. Now we're going to have an inflection point where the graph changes concavity. So that has to be from concave up to concave down, or concave down to concave up. Well, our graph is concave down from 0 to 3, the graph of f, that is, not f prime, but the graph of f. So it's concave down from 0 to 3 and then switches to concave up at 3. And then we don't have any other switches from concave down to concave up or vice versa. So for inflection points, it would be the point on the graph of f where x is equal to 3. All right, now we are ready for the second derivative test. Now the second derivative test isn't telling us about concavity. That's the concavity test. That was an earlier theorem. But the second derivative test tells us about critical points and whether we get a local max or local min. So if we have a critical value, remember we find critical values by finding where the first derivative is 0 or does not exist. In order to use the second derivative test, the second derivative has to be defined at that critical value. And if it's positive, then there's a local min. And if it's negative, there's a local max. So we're going to look at an example now. We are going to find the local max and local min of the function f of x equal 2x cubed minus 3x squared minus 12x using the second derivative test. So again, pause, follow the link to the YouTube video for this example, and then we will continue after the video. Our next example. These two examples, this one and the next one, are really about graphing. We've been talking a lot about what the shape of the graph looks like. These two examples are going to bring together the things we've been talking about in the last lecture and this one, where we're talking about increasing and decreasing from first derivative information and concavity, concave up and concave down, from the second derivative information. So in this particular example, we're going to sketch the graph of a function that satisfies all of these conditions, and we've got a lot of them listed. So we're going to go through those conditions, and then we're going to sketch a graph. There are many possible correct answers here. Before you pause for the video, I just want to go through some of the conditions here. I just want to highlight at the beginning, we've got two different things going on. The f of 0 equals 0 gives us a point on the graph. The f prime of 0, f prime of 2, f prime of 4, f prime of 6 equals 0. Those give us critical numbers. And then this last bit down here before we go to the video, f of negative x equal f of x. This is telling us that this is an even function, which means it is symmetric across the y-axis. So we're going to figure out what the function would look like on one side of the y-axis, and then we are going to reflect that across the y-axis to get the rest. So you should pause now, go watch the video, and then come back for the last example. Okay, last example. This time we have the function f of x equals 3x to the fifth minus 5x cubed plus 3. We're going to find the intervals of increase and decrease, the intervals of concavity and the inflection points, and then we're going to put all of that information together and sketch the graph. And when we find the intervals of increase and decrease, we are also going to find any local max or local min at the same time. So pause here, follow the link to the YouTube video for this example. The link's in Blackboard as usual. And if you're in the slides without narration, then you're not hearing my voice, but you can follow the link directly from the slides.